Batrisyia binti Rizal, and this is the video presentation for my final year project of this session. The title of my final year project is Visualization of the Deuteron structure using Python. There are two main objectives of this work, which are, firstly is to solve the transcendental equation numerically to show the relationship between the depth of the potential well and the mean nuclear radius. The second objective of this work is to visualize the radial probability distribution for any central potential, which in this work we use the radial wave functions for the three-dimensional simple harmonic oscillator. We use Python 3 to solve and visualize the Deuteron structure. Here's a brief description of the work done for this final year project. Firstly is solving potential using Schrödinger equation. We use the transcendental equation to solve the potential of the Deuteron. The transcendental equation is obtained from the Deuteron wave functions at the boundary of r equals to 2.1, in which is the Deuteron radius. The transcendental equation was solved numerically to obtain the wave numbers k1 and k2, in which are required to plot the smooth radial wave function of the Deuteron. Next is the spherical harmonics. Spherical harmonics was obtained from the angular part of the separable solutions for the three-dimensional Schrödinger equation. Here are the results obtained for this work. There are two states of the Deuteron in which, in regards of the angular quantum number L of 0 and 2, the values 0 and 2 are chosen is actually to retain the Deuteron's parity of 1. As for the first structure here, this is L0 and ML0. ML is the magnetic content number of the Deuteron. And this structure here is the S state of the Deuteron. The spatial probability distribution shown here is a spherical symmetrical structure which has a quadruple moment of 0. This is the main structure of the Deuteron. As for the L equals to 2, this is the D state of the Deuteron. Then there are three possible structures under the D state of the Deuteron. These three structures are obtained from the different values of the magnetic quantum number of ML. The possible magnetic quantum numbers for the Deuteron D state are 0, 1, and 2. As for the ML with the value of 0, the spatial probability is larger around the z-axis relative to the spatial probability around the x-axis, which indicates the quadruple moment of the structure is more than 0. As for the ML of 1, the structure is symmetrical and has equal sizes of plotting diagonally. This symmetrical structure indicates the quadruple moment of this particular structure is 0. As for the ML of 2, the spatial probability distribution is only formed around the x-axis, and this has the smallest spatial probability shape compared to the rest of the structures. The quadruple moment here is negative, but probably a very small value as compared to the second structure. The total quadruple moment of the Deuteron is actually the summation of the individual quadruple moments from each of the Deuteron structures, and the experimental quadruple moment for the Deuteron obtained is actually a positive value. The individual spatial probability distribution has shown different quadruple moments, and the individual quadruple moments is actually tally with the experimental value of the Deuteron quadruple moment. As for the Deuteron structures in the D state, they are all at minima at the origin or the center of the Deuteron structure, which means nucleons are getting farther away from the center of the Deuteron and goes upwards. The similarity here for all the spatial probability distributions of the nucleons in the Deuteron is all plots have at least two axes of symmetry, which means either of the nucleons will be at the opposite side of the plot or the structure. This is on par with Pauli's exclusion principle for fermions. Protons and neutrons are fermions. Pauli's exclusion principle for fermions states that no two fermions can ever be at the same quantum state, which in this case, the spins of the nucleons may differ as different positions is occupied by either of the nucleons. So that is all from me. Thank you for watching.